Hi class, we continue the last lecture about the Milky Way. So this is the Milky Way part 2. Okay, so about the dark matter. So the Hubble Space Telescope, HST, observed many of the globular clusters in the galactic halo, were located in here. And this is the zoom in image of this white area here, and shows the star formation is much less frequent below a cutoff at 0.2 here. Okay, so here we can see the star formation which less frequently appear, and this rules out the possibility of the red dwarf as a dark matter, since they are unexpectedly rare in the galactic halo. So radically different alternative is the dark matter is made up of the exotic subatomic particles, which is must have mass but must also interact hardly at all with normal matter. And we have the weakly interacting massive particles that propose to be the dark matter particles that produce in abundance during the earliest moments in our universe, but so far have not been detected. So, and also they have suggested the modification to the Newton's law of gravity that increases the gravitational force, that the Fg, okay, on the galactic scales. For example, we have the modified Newtonian dynamics, MOND, and the tensor vector scalar is the Davis gravity work differently at the low acceleration. So the searching for the stellar dark matter, we can see from this figure here, the distribution of this stellar dark matter may be observed through the gravitational lensing. So it's caused the temporary but substantial brightening to 5 times at the distant star. Okay, and also referred to as a gravitational lens. Yeah, and their mass, distance, and speed will affect the amount of the brightening. And as we can see in this figure, the lensing object that passes in front of our field of view from top to the bottom. Okay, let's say this star. So light from the star, say, so the observer here. So the object look fainted, the foreground object. Okay, and see here the result. And for the next one, for more light reach the eyes, so have the affected by the gravitational lensing. Okay, so the lens star will be seen like here, and also the last one. So we can look at, we can observe the distribution like this. So basically, the type of the dark matter exists is the mixture of the baryonic and the non-baryonic matter. As you can see this figure, you can see it's like just the same figure of the distribution. Okay. Okay, also about the galactic center. Okay, is the general direction of the constellation of Sagittarius that should be densely populated with billions of stars. So the infrared image shows the galactic center is a dense cluster of 1 million stars times greater than our solar neighborhood. So this one is the galactic center has a complex structure and many ongoing violent activities such as here, okay, the infrared, okay, and if we see from the radio, okay, we see intense and using a complex structure, okay, and also this one and this one. So the galactic activity okay, from this galactic center is the brightest radio source in the constellation Sagittarius. The extended filament can be seen on a scale of this and caused by the strong magnetic field. So for the infrared observation of the galactic center show a huge cloud rich in dust, and for the radio observation indicating that a ring of molecular gas across containing some of the material that rotates around the galactic center. And also we have the rotating bar at the galaxy central. Okay, and within the ring is a rotating disk of a molecular gas with a streams of matter. And for the X-ray observation by Chandra, show the extended region of hot gases that associated with the supernova remnant. And also we have the Doppler broadening of infrared spectral line emitted from the central of a galactic center. And this suggests that whatever is at center must be extremely massive, okay, so called the supermassive black hole. The energy emitted by the infalling matter from the accretion disk around the hole is the source of the high energy radiation. And the strong magnetic field generated with the accretion disk as matter spirals inward act as a particles accelerator, creating the extremely high energy particles detected on Earth as cosmic ray. Okay, this one is the VLBI observation using radio telescope. I think you have I've mentioned this in the previous lecture, in the previous chapter. And using the advanced adaptive optic technique, high resolution of infrared image of the innermost of galactic center was obtained. And then we have the central black hole, where the image quality is good enough that the proper motion of the several of stars are clearly seen. Okay, for example, one of the brightest star S2 here can be seen by this image, good quality of image. Okay, bright source with a 10-minute period is detecting orbiting very close to Sagittarius. We can see this video. Okay, so it could be a hot spot on the accretion disk that circle the SMBH. Yeah. So this size of event horizon should be, which is only resolvable via the VLBI. Okay, so for the next one, okay, the galaxy core, the resolution increasing by a factor of 10. Okay, so this one, what you can see in the video just now. Okay, so the spiral pattern here, okay, in the middle, the accretion disk. Okay, so the ring of gas is visible. It's a giant molecular cloud, and the pink patches is the emission nebula. So the pinkish iris gas surrounding the reddish heart of the galaxy, it means the energy of a million supernova And the young dense star cluster are evidence of the recent star formation. Star forming ring, and yeah, and also the white hot disk of gas around a black hole with the remains of the disrupted star cluster. So you can see every different pattern here with the different in their distance, 5 kpc, 50 and 500, and you can see the changing of the color also. Okay, so that's all for this chapter. Thank you.